Hey guys, today we're going to look at the integration of composite functions. Now there are several ways for which we can integrate a composite. Now just as a reminder, a composite function is when you have a function within a function. So typically composite functions consist of trigonometric functions, anything with e or ln, or if you have a binomial raised to a high exponent. So these would all be considered composites. Now, in order to kind of figure out how to integrate these, we're going to examine these three functions here, take the derivative, and then see if we can find its integral. So for the sine of 3x, when we take the derivative, we take the derivative of the outer function, which is sine, which would be cosine of 3x. And then we multiply by the derivative of the angle, which is 3. So this gives me 3 cosine of 3x. So that, remember, this is the chain rule. So now when we integrate that derivative, that's 3 cosine of 3x dx, we see here that if we were to see this originally, we'd be like, what the hell do I do? But basically, this 3 is the derivative of 3x. So that means that its antiderivative must have been sine of 3x, and then of course the plus c. Now you may not be able to recognize what to do yet because we've only done one example, so let's keep going and then I'll break this down even more. When we take the derivative of e cosine of x, what we do is for e we copy down the function, so e cosine of x, and then we multiply by the derivative of the angle, which is negative sine of x, which gives me a final derivative of negative sine x times e raised to the cosine x. Whichever way you choose to write it is fine. So if we saw that in an integral, it would look like negative sine x times e cosine x dx. And what you would have to do is recognize that negative sine of x is the derivative of of the cosine x. So when we integrate, my answer would just be e cosine x plus c. So a lot of this is just pattern recognition, is noticing that it's knowing your derivatives well enough that you can look at a function and say that this must have been the derivative of this function. So now let's look at this one here. The derivative of the ln of x squared plus 3, when you're finding the derivative of ln, you take the derivative of the inside of ln, so 2x, and you put it over whatever originally was inside, so x squared plus 3. So if you saw that in an integral, it would be 2x over x squared plus 3 dx. And you would have to recognize that 2x is the derivative of the denominator, and if that happened, my answer would be ln of the absolute value of x squared plus 3 plus c. Now you may be wondering why I put this in absolute value, and that's because whenever you're taking the integral of a function that is ln, right, remember that ln is only defined for as long as whatever is inside of ln is greater than 0. So we put the absolute value to indicate that what's inside of ln has to be greater than 0. Because remember, when we see this, we did not know what the original function was. Now, how does this work? Okay, there's a lot of blue going on here and it's a lot of notation. But basically, when you're taking the derivative of a chain rule function, what you do is you take the derivative of the outer function, you leave the inside alone, and then multiply by the inner function, your chain rule. That means that if we saw this written backwards, if you have the derivative of the outer function, and then you see that the g prime of x is multiplied to it, then that means that when you integrate, you're only really integrating the outer function, that f prime of x. So that's why you see here that we basically just ignore the g prime, and when we integrate f prime, it would just be f and then the inside, which is g of x plus c. So that g prime of x allows us to integrate f prime of g of x. So it's kind of like your license to integrate. So let's see if we can work this out. We have here 3x squared times x to the third plus 4 raised to the fifth. What you do is you have to identify what is your inner function. My inner function is x to the third plus 4 because that's what's inside of the parentheses. The derivative of x to the third plus 4 is 3x squared, which is here. This is my g prime. So basically I just ignore it, and the only thing that I'm really integrating is the outer function, which is this to the fifth. Because that's just a power, what we're going to do is add 1 to the exponent and then divide by the new exponent. So my answer here would be x to the third plus 4, because we don't do anything to the inside, raised to the 6, put it over 6, and then plus c. And this would be our answer. Now let's look at this one here. We have 2 sine of 2x plus 3. My inner function is the 2x plus 3. 2 is my g prime, because that is the derivative of 2x plus 3. So I can basically ignore this, and then I'm going to integrate only the outer function, which is sine of x. And the antiderivative of sine is negative cosine, and then you leave the inside alone, so 2x plus 3 plus c. And that would be my answer. Now this one here may be a little bit harder to integrate, but let's rewrite this. This is the same thing as saying the integral of 2x times x squared plus 5 raised to the 1/3 dx. Now the derivative of my inner function is 2x. So since it's multiplied by that g prime, I can basically ignore this and only integrate the outer function, which is the 1/3. So I'm going to add 1 to that exponent. So I'm going to add 3 over 3, because that's 1/3 plus 1. And that would give me x squared plus 5 raised to the 4 over 3. And then I divide by 4 over 3, which is the same thing as multiplying by the reciprocal, plus c. Over here, I have 2x plus 2 over x squared plus 2x. Whenever you see a fraction, the first thing I do is I check if the numerator is a derivative of the denominator, which the derivative of x squared plus 2x is 2x plus 2. So if that's the case, then that means that this is ln when the derivative is in the numerator and the original function is in the denominator. So this is going to equal to the ln of the absolute value of x squared plus 2x plus c. And that would be my answer. And if you're unsure ever of any of your answers, then what you can do is take your antiderivative and take its derivative, and it should equal to exactly what's inside of your integral. Now we're going to look at a couple examples where we may need to do something to the integral so that I can be able to integrate. In this first one, I have the cosine of 3x plus 2. I would initially look for the derivative of my inner function. What I'm missing here, the derivative of 3x plus 2 is just 3. So I'm missing the 3 to be able to integrate. So what I do is that I multiply 3 in here, so that way I could integrate my function. But I got to keep this integral balanced. So if I multiply 3 in my integral so I can integrate, I'm going to have to then also divide by 3 on the outside. Since 1/3 times 3 is just 1, and multiplying anything by 1 is fine. So this 3 now allows me to integrate my cosine, and basically I can just ignore it. So I have this 1/3 on the outside. The antiderivative of cosine is sine. And then I leave the inside alone. And then, of course, the plus c. So this would be my answer. Now over here, I have 3x times the square root of x squared plus 2. Now I'm going to rewrite this so that way we have the power rather than the root. So this is 3x times, I just did that, I'm just kidding. The whole point was to rewrite it. So this would be x squared plus 2 to the 1/2 dx. Now the derivative of x squared plus 2 is 2x, but here I have 3x. So what I'm going to do is I'm going to move the 3 to the outside. So this is 3 the integral of x times x squared plus 2 to the 1/2 dx. And now what I need is a 2 here in order for this to be the derivative of my inner function. So I'm going to multiply by 2 and at the same time divide by 2 on the outside. So that way I keep everything balanced. And now I am allowed to integrate. So basically I can ignore the 2x and I'm just going to integrate the outer function. I have a power, so I have to add 1. And 1/2 plus 1 is 1/2 plus 2 over 2. So I get 3 over 2 from the outside here times x squared plus 2 raised to the 3 over 2. And then I have to multiply it by the reciprocal because I need to divide by 3 over 2. So the reciprocal of 3 over 2 is 2 over 3 plus c. Now the 3 over 2 and the 2 over 3 basically cancel out. And so my final answer is x squared plus 2 raised to the 3 over 2 plus c. Let's try another one. We have here 5e raised to the 3x dx. The derivative of my inner function is 3, but what I have here is a 5. So I'm going to move the 5 to the outside, which is 5 integral of e to the 3x dx. What I need to integrate is a 3. So I'm going to multiply 3 here in the inside of my integral, meaning I have to divide 3 on the outside. So now I can ignore the 3 and just integrate e to the 3x, which, remember, we're just integrating the outer function, which is e, and the integral of e is just itself. So my final answer here would be 5 over 3 e to the 3x plus c. Now over here, what I have is 3x raised to the square root of 3x over the square root of 2x squared plus 3. Now this is not the same as ln because we have this radical here. So what we're going to do is we're going to rewrite this using the power. So this is the integral of 3x times 2x squared plus 3 raised to the negative 1/2 dx. So remember, the square root is the exponent 1/2. It's in the denominator, which is why I made that exponent negative. Now the derivative of my inner function here is 4x, but what I have is 3x. So same as the other ones, I'm going to move this 3 on the outside. So this is 3 times the integral of x times 2x squared plus 3 raised to the negative 1/2 dx. Like I said, the derivative of my inner function is 4x, which is why I keep the x here anyway. And remember, the only thing you can really move outside of the integral is any constant. So I'm going to multiply here a 4, so that way it is the derivative of my inner function, meaning that then on the outside of my integral, I have to divide by 4. So now I'm just going to add 1 to this exponent. So adding negative 1/2 plus 1 will be plus 2 over 2. So I can ignore this, right, because I've already working on this process. So we have 3 over 4 times 2x squared plus 3 raised to the 1/2, because negative 1 over 2 plus 2 over 2 is 1/2. And then divide by 1/2 is the same thing as multiplying by the reciprocal, which is 2. And then plus c. I can now simplify this 3 over 4 and the 2, right? So this 2 can cancel and this will now become a 2. So this, my final answer, is 3 over 2 times 2x squared plus 3 raised to the 1/2 plus c. And you can also rewrite this as 3 over 2 times the square root of 2x squared plus 3 plus c. So this is by using pattern recognition. and by multiplying constants. If you understand this concept, it goes a long way because it makes the process of integrating composite functions much easier. However, it only works if what you're missing for the derivative is a constant. So, because I can't just multiply something that is not a constant, because then that would mess up my integration. So if that's the case, then we would need to use another method. And this method also works if you don't understand pattern recognition. So this method can be used for all composite functions if you prefer. However, it is more time consuming. So let's go over this. We have here the integral of x times 2x minus 1 raised to the third power. So first of all, we're going to break this down so that way you can understand why we're going to use this method. My inner function here is 2x minus 1. G prime, which is, remember my inner function is defined as g of x, so g prime of x is the derivative of my inner function, which is 2. If I look here, is 2 part of my integrand? Aside from the inner function, no, because instead I have an x, so no. And I can't just multiply x by a constant to get 2, so no. So if that's the case, we're going to have to use u-substitution. Now I have here the guidelines of how to use u-substitution and what we're going to do. So I'm going to read this out and then we're going to practice a couple of questions. First, what we're going to do is we're going to let u equal to the inner function. And then we're going to find du, which is basically the derivative of u, and solve the equation for dx. And you'll see what I mean when we look at the example. Then we're going to find an expression for x in terms of u. We're going to rewrite the entire integrand as a polynomial type function in terms of u that would then allow us to integrate. Once we're done integrating, we substitute u back to g of x. So this is how that works, because I'm sure that just by me reading that, you're probably still like, I don't know what's going on. So this is the same example that we were doing before. U here is 2x minus 1. X, if I use this equation here and I solve for x, we have that u is equal to 2x minus 1. So I'm going to solve for x. So I'm going to add 1 to both sides. We get u plus 1 is equal to 2x. And then divide the 2. We get that x is equal to u plus 1 over 2. du is the derivative of u. So when I find the derivative of u, it would be 2, and the derivative of x, which is dx. So that means that dx, if du is equal to 2 dx, if I divide by 2, dx is equal to 1/2 of du. So now what I'm doing here is I'm going to get my integral here and I'm going to substitute everything using u. So I have the integral, I have the expression for x, which is u plus 1 over 2, times 2x minus 1 is u. So this is u to the third. And then dx is 1/2 du. So now my integral is entirely in terms of u. And now we just got to do a little bit of algebra to help us find that integral. Now we have this 2 in the denominator and this 1/2. These are constants that we can just move out. And I'll explain to you how. This is the same thing as saying as 1/2 of u plus 1 times u to the third times 1/2 du. See what I mean? This 1/2 and this 1/2 are constants that are being multiplied to the entire integral. So I can multiply them together and move it to the outside. 1/2 times 1/2 is 1 to the fourth. So now what I have in my integral is just u plus 1 times u to the third du. Distribute the u to the third, and this is 1 over 4, the integral of u to the fourth plus u to the third du. I can integrate this. This is a polynomial type function. So we have 1 over 4. U to the 4th is u to the 5th over 5, plus the integral of u to the 3rd is u to the 4th over 4, plus c. We can distribute this 1/4, and this is u to the 5th over 20, plus u to the 4th over 16, plus c. I'm essentially done integrating. Now that we're done, we can substitute u back with what it represents, which is 2x minus 1. So my final answer would be 2x minus 1 to the 5th over 20, plus 2x minus 1 to the 4th over 16, plus c. And that would be my final answer. Let's try that again. We have here 2x plus 1 over the square root of x plus 4. Now sometimes you gotta get a little bit creative, but it's still very important to be able to identify what is your inner function. What we have here, since we have a square root, the inner function I'm going to use is the x plus 4, since it's inside of the square root. So u would be x plus 4. Now remember, we need to find an expression for x. So if u is equal to x plus 4, I would subtract the 4 to both sides, making x equal to u minus 4. Now du is the derivative of u. So that would be the derivative of x, which is dx plus 0. So dx. That means that dx is equal to du. So they are both equal to each other. So now we're going to rewrite this integral. And like I said, you have to kind of get a little bit creative. We have this 2x plus 1. But I have an expression for x. So I'm just going to substitute x with u minus 4 and then distribute the 2 and add the 1. So this is going to be 2 times x, which is u minus 4, plus 1, over the square root of x plus 4, which is u. And then dx is du. So now everything is in terms of u. We're going to distribute this 2 and then combine like terms. So this is going to be 2u minus 8, and then plus 1 would be minus 7, over u squared, which is u to the 1/2. Now I can bring this up, the u to the 1/2, and that would be the integral of 2u minus 7 times u to the negative 1/2. Since when I bring it up, remember, since all of it is being divided, then that means that all of it will have to be multiplied. So I'm going to distribute, sorry, I forgot the du. I'm going to have to distribute the u to the negative 1/2 to both of these terms. When you distribute, remember what you're doing here, 2u times u to the negative 1/2, you have to add those exponents. So this is 2u raised to the first, or 2u raised to the 2 over 2 to allow you to add the exponents. So that would be 2u raised to the 1/2 minus 7u raised to the negative 1/2 du. And now that we have a polynomial type function, we can integrate. So we have here 2u raised to the 3 over 2, since I have to add 2 over 2, times the reciprocal, which is 2 over 3, minus 7u to the 1/2, because again, I'm adding 2 over 2, and negative 1/2 plus 2 over 2 is 1/2, times the reciprocal of 1/2, which is 2, plus c. Let's simplify this a little bit. We get 4 over 3 u to the 3 over 2 minus 14 u to the 1/2 plus c. So my integration is done. I can now substitute u back with the x plus 4. So this is 4 over 3 x plus 4 raised to the 3 over 2 minus 14 times x plus 4 raised to the 1/2 plus c. And this would be my final answer. Now, let's look at, whoops, going backwards a second. Now let's look at using pattern recognition versus u-substitution, and how do you recognize between what to do. So basically, when you're trying to figure out what works out, or like I said, u-substitution will always work. However, pattern recognition is a much more efficient and faster way of being able to integrate. So when we have here the integral of cosine x times the square root of sine x, you can definitely use that u is sine x and go through that whole process. And you'll get the right answer. It's just a little bit more time consuming. However, I do notice that cosine of x is the derivative of sine x. So this gives me the license to integrate just the outer function, which is the square root. So basically, I can rewrite this as the integral of cosine x times sine x raised to the 1/2 dx. I can ignore the cosine x since it is the derivative of sine of x to the 1/2 of sine of x. And now I just apply the power rule. So I'm going to add 2/2 to this exponent, which would be sine x raised to the 3/2, and then multiplied by the reciprocal, which is 2/3 plus c. See, this is much faster. This is my final answer. If you were to use u-substitution, it would take you a couple more minutes, which, in terms of the AP exam, can be, those minutes are precious. Now let's look at this example. We have here the square root of x minus 1 squared all over the square root of x. Now, in this particular example, to figure out what is the inner function may be a little bit more difficult since we have these square roots, and typically when we see a square root, we think what's inside of the square root would be u. However, we have this parentheses around, and this is that square root of x minus 1 is inside of that exponent. So that's what I would assign as u. U is going to equal to the square root of x minus 1. So now when I find du, right, this is the same thing as saying x to the 1/2 minus 1. So du is going to equal to 1/2 x raised to the negative 1/2 dx. Because remember, in terms of when you're finding du, whenever you have the derivative of, or whenever you're finding the derivative of x, you have to then attach the dx. And then the derivative of negative 1 is just 0. So du can be simplified to be 1/2 square root of x and then dx. So dx, right, all I would have to do to solve for dx would be to multiply the 2 square root of x. So dx is going to equal to 2 square root of x du. So now that I have u, I have du, and I have dx. Now notice I didn't necessarily solve for x, and that's because I don't really need to. Some examples you don't need to solve for x when you're using u-substitution. I normally don't solve for x. I did in the previous examples just in case, but you'll see examples later when we do need to solve for x. I mean, it doesn't hurt to anyway. Like if you don't substitute it, it's not a big deal. So here, the square root of x minus 1, that is u, so the integral of u squared over, and then the square root of x, I'm just going to leave it. And the reason why I leave it is because when I substitute dx, I'm going to multiply by 2 square root of x du. And what happens here is those square roots of x, they basically cancel out. So that's normally what I do, is I don't necessarily solve for x like I did in the previous examples. And then once I plug in, if my x's don't cancel, if I do have any x's left over, then I would go ahead and use u to solve for x and then substitute. But here it canceled, so it worked out great. So this is equal to the integral of 2u squared du. Now this is simple to integrate. You just add 1 to the exponent and then divide. So this is equal to 2u to the 3rd over 3 plus c. And now I replace u back with the square root of x minus 1. So my answer would be 2/3 square root of x minus 1 to the 3rd plus c. And this would be my answer. Now we're going to look at how to use u-substitution for definite integrals. And it's basically the exact same thing except one extra step. So here we have the integral from 0 to 3 of x over the square root of x plus 1. I'm going to make my inner function, which would be the x plus 1, because that is inside of my square root, and I don't have any other additional parentheses to worry about. X, I would just have to subtract the 1 to solve for x, so x would equal to u minus 1. So here I did solve for x, and again, you can always solve for x, and if you don't end up using it, you don't. Du is going to be the derivative of x plus 1, which is just dx. So that means that dx is equal to du. Now we have our limits of integration. When we are integrating in terms of u, you can do one of two things. You don't necessarily have to do this part here, because then you can substitute what u is equal to, and then like substitute it back with the x's and then plug in your original limits. However, that takes more time. So it may be easier for you to solve for what u is equal to get our new limits of integration. So when x is equal to 0, and what I'm going to do here is, here's x. I'm solving for u, so I'm going to plug in x here. So when x is 0, 0 plus 1, u is equal to 1. When x is 3, 3 plus 1, u is equal to 4. So now we're going to rewrite this entire integral. Instead of 0 to 3, I am using 1 to 4. We have that x is equal to u minus 1 over the square root of u, and then dx is du. Now this I can rewrite as the integral from 1 to 4 of u minus 1 times u raised to the negative 1/2 du. So I brought that u up. Remember, since everything is divided by the square root of u, when I bring it up, everything must be multiplied by u raised to the negative 1/2. I'm going to distribute, and I get here u to the 1/2, since 2 over 2 minus 1/2 is 1/2, minus u to the negative 1/2. And we're integrating that from 1 to 4 du. Now let's integrate. So we have here, we have to add 1, so 2 over 2 plus 1 over 2 is u raised to the 3 over 2, multiplied by the reciprocal, which is 2 over 3, minus, add 2 over 2 to negative 1/2, that would be u to the 1/2, times the reciprocal, which is 2. And am I evaluating that from 1 to 4? So now we plug in 4, so we get 2/3 times 4 raised to the 3 over 2, minus 2 times 4 raised to the 1/2, minus, now I plug in the 1, 2/3 times 1 raised to the 3 over 2, minus 2 times 1 raised to the 1/2. Now we have to know how these exponents work. Remember that you can always rewrite this with the radical and the power if that makes it easier, but if you want to like kind of shorten your time, remember that the denominator is the root and the numerator is the power. So if the denominator is a root of 2, that means the square root of 4 and then to the third. So we have 2/3. The square root of 4 is 2, and then 2 to the third is 8, minus 2, and then this is 1/2, which is just the square root. So the square root of 4 is 2, minus anything, 1 raised to any exponent is just 1, so this is just 2/3 minus 2. Now this gives me 16 over 3, minus 4, minus 2 over 3, plus 2. So what I did was I just distributed the negative so I can combine what I can combine, and then I'll do my least common denominator. So 16 over 3 minus 2 over 3 is 14 over 3. So let me fix that. And then negative 4 plus 2 is negative 2. So I'm going to need to put this over 3. So I need to multiply this by 3. So this is 14 over 3 minus 6 over 3, which gives me a final answer of 8 over 3. And that's how you can use your u-substitution with those limits of integration. Let's try a couple more examples. We have here 1 to e squared of the ln of x squared plus 1 over x dx. So here what I'm going to do is I'm going to use u as my inner function, which we see here this parentheses squared. So my inner function is going to be the ln of x. That means that du is going to equal to 1 over x times dx. And so dx, I would have to just multiply x to both sides, would be x du. And notice here again, I didn't necessarily solve for x. And usually I just don't until if I absolutely need to, meaning that x's won't necessarily cancel. So this is a definite integral, so we'll also need to rewrite those limits. So when x is equal to 1, u is going to equal to, now I plug it in here, u equals to the ln of x, which is 1. The ln of 1 is 0. Now when x is equal to e squared, u is going to equal to the ln of e squared, which ln and e would cancel, so u would be 2. So now let's rewrite this integral. This is my integral from, instead of 1 to e squared, it would be 0 to 2 of u squared plus 1 over x times dx, which is x du. And see again here, my x's cancel. So I don't necessarily need to solve for x, which is again why I do that. So what this gives me is the integral from 0 to 2 of u squared plus 1 du. This is much easier to integrate than this hot mess. So when I integrate u squared, that would be u to the third over 3 plus u. And I'm going to integrate that or evaluate it from 0 to 2. So we plug in 2, we get 2 to the third, which is 8 over 3 plus 2 minus, if I plug in 0 to both of these, it's just 0. So we're just going to combine the 8 over 3 plus 2. So I'm going to put this over 3, multiply this by 3, and we get 8 over 3 plus 6 over 3, which is equal to 14 over 3. Now let's do this final example here. We have the integral from negative 1 to 1 of x plus 1 over x squared plus 2x plus 2 raised to the third. So u here is going to equal to my inner function, which is x squared plus 2x plus 2. That means that du is going to equal to 2x plus 2, and then all of that dx. Now, what I can do, well, I'll do that later. So dx, I would have to divide, so that would be 1 over 2x plus 2 du. So I have my information here. I'm ready to plug in. Oh, except I need my new limits of integration. So let's do that. So when x is equal to negative 1, u, now I plug in negative 1 here, negative 1 squared is 1, plus 2 times negative 1 is negative 2, and then this negative 2 would cancel with this 2, so I just have 1. And then when x is equal to 1, I get 1 plus 2, which is u would give me 5. So now we're ready to plug everything in. We have the integral here from, instead of -1 to 1, we're using 1 to 5. Now I didn't solve for x, so I'm leaving this x plus 1 over x squared plus 2, all of that is u to the third, times dx, which is 1 over 2x plus 2 du. Now the reason that I left it here like this is that if you look at that denominator, we can factor out a 2. So this is 1 to 5 of x plus 1 over u to the third times 1 over 2 x plus 1 du. See, this x plus 1 cancels with this x plus 1. And then we're left here with just this 1/2 that is a constant. So this 1/2, we can move it here to the outside. So now my integral would be 1/2, the integral from 1 to 5 of 1, all that's left is 1 over u to the third, which is u to the -3 du. So we add 1 to the exponent and divide by the new exponent. We get here 1/2 from that outside of u to the -2 over -2, and we're going to evaluate that from 1 to 5. Let's rewrite this so it's a little bit, nicer. This is 1/2 on the outside of -1 over 2u squared. And again, we're evaluating that from 1 to 5. So I'm leaving this 1/2 on the outside. I'll distribute that later. We're going to plug in the 5. So this will be -1 over 2 times 5 squared, which is 25. 2 times 25 is 50, minus negative, so it'll become plus 1 over, and then 2 times 1 squared would just be 2. So I'm going to need a common denominator here to add this together. So I'm going to multiply 25 to both. So that way the denominator would be 50. So I get 1/2 times -1 over 50 plus 25 over 50, which gives me 1/2 of 24 over 50, which gives me a final answer of 24 over 100, which of course we can simplify by 4, which gives me 6 over 25. And this would be our final answer. And that's integration of composite functions.